intuition you have in a Markov chain in Rn. There's physics, right? Imagine if somebody gave you the equations for an airplane or a car, and you've got these smooth dynamics and all that, and then suddenly you have to discretize the state space and get a state transition diagram, and all the continuity's gone. The idea of states being near each other is gone. I mean, I guess it's sort of encapsulated by the probabilities being large. But I don't see much value at all in sticking to finite state spaces, and so we won't look at them much at all. And it's not even true. People say, "Well, for computation, of course, you're going to go to finite state spaces." Bullshit. Not at all. So this course is unique in that sense. It's really unusual just to blow off the finite state space, even though, in homework we'll look at it. Man, we have to stop in 15 minutes? Oh, damn. Well, 2 is optimal control. And I will say a few things. For that we have a input. So all we do is we take the same dynamic equation. This is called a state space equation, by the way. And that's a state space equation as well, but with an input, right? And now, basically, the question is we'd like to be able to synthesize inputs. So we want to find good control laws. So. Typically that's what you do, That's the beauty of these Markov models, is that it turns out that for many, many, many objectives, you can choose your input to be some static function, this is a feedback law, of the state, and do beautifully, and basically the optimal sequence of U of t's over all possible inputs can be given by just static feedback law. Now, the equations to find phi, it's basically our friend again. So there's basically a refinement of Lyapunov theory is how you find a good phi. And what those refinements are, let's erase the finite state space here. Somebody tell me, 1, 2, 3, what's the refinement?
4.
4, that's good. So what kind of refinements of Lyapunov theory would be used to find good policies for controlled Markov chains? If you've taken like a linear control course or a nonlinear control course, or you had some background in control at all, no? All right, cool, that's great. You don't need this background, but the Bellman equations. So that's basically what a lot of what part 2 of the course is about, is understanding these Bellman equations, how they relate to the Lyapunov equations, and you get these really nice formulas that give you the control law phi. Okay, and they're beautiful, elegant, wonderful, but they give you no computational tools at all. And so it's very much like what happened with communications. So Shannon built this magical theory for capacity of communication channels and what was achievable and all of that. And then suddenly we had, wireless coming, and all these people in information theory had been out of work because there was nothing to do. All the theory had been done. I was at Illinois in the 90s, and that was a big center for stuff. Suddenly, yes, you heroes, you've got all the machinery, you go and solve these problems. And there was nothing from statistical information theory, almost nothing that could be used for actually computing good codes for communicating. And so it took a bunch of other people, mathematicians and computer scientists and other engineers, to create the algebraic codes and all the hacks that turned out later could be proved to be almost optimal in terms of capacity. So here we're in the same situation where Bellman and Russian scientists created a beautiful theory for what's achievable, but nothing about computation. And then we get to part 3 of the course, is that somehow we need to approximate. There's no way to solve these equations that would give you even a good policy. I mean, I suppose I don't want optimal. I just want a good policy. I want it to be stable, or 50% of optimal. And no matter what, the computational complexity is insane. But you need to approximate, and we have one approach, is these reinforcement learning techniques. So that's part 3. I'll just write it like that. So once we get to that, we can go around and RL is the main thing people run to at the moment. It's something else. You can go and say, well, go to continuous time, and people have partial differential equation techniques they've developed for problems that aren't too big. But if you go to problems in finance, can you imagine how big the state space is? Can you imagine writing this for the stock market? What do you think X of t would be? I want to make money in the stock market. What's my state?
Returns at the end of the day.
Returns, that's one thing. All the returns in the stock market. What else? And that's the thing. These idiots actually just use that alone. They do. I mean, it's changing now, but they have in the past. What else? I can't believe nobody's seen Trump's tweets. No, it's true. I mean, you put in the probability that Tehran is bombed tomorrow. I mean, there's so much information you'd want to put in that X of t. It is so abstract. And can you imagine being so gullible that you have the Markov property? You'll pretend it does, but no matter what, it's going to be massive if you're going to do it right. And so you need some approximation methods. And right now we're sort of stuck with reinforcement learning, and I'll give you a bunch of flavors of that through the course. And that's going to be, all of this will be fun, I promise. I mean, some of it will be tough. And I hate the fact that, what do you do? I mean, Jose, how do you handle this? Nobody wants a linear course where you start off with the basics of Markov models, and everybody's saying, no, I want to get to something real. And then you get to optimal control, and it gets to seem real, but then I tell you, nothing's computable, it's worthless. And then we get to April, and I give you RL, and you get to actually code things and make things work. So that's what I mean about having to somehow flip this. I'm going to have to somehow introduce this stuff a little bit earlier somehow, and have you play around before we get to it. And I've been saying that for 25 years, and this year, this will be the year. Okay, so I think that's it. I think we're out of time. I mean, I can't get in. I wanted to say more about this, but I'll wait till next time. So I'll be around for questions. I'm sure there's lots of them. So unless there's something is there a general question about the course? About books, like I said, there's no good book for the course, but I've been developing handouts for over 25 years, and I refine them every time I teach the course. So basically, there's a book that I'll be handing out in pieces. And the last part of the course, my former PhD student Aditya Devraj and I just finished a big book chapter, which is like made for the course. So it's like you've got a book for the last part of the course. Any questions? All right. Until Thursday.